All right, guys, we're going to cover the final example in chapter 13, section 3. And again, ignore the example 14.5 in my notes. These are written for your new textbook. This is example 13.5 in your online textbook, which is on page 431 of it. And this is a good problem that uses an old idea just in SHM of energy and momentum together. If you recall, way back when we did energy and momentum, that's both energy and momentum, especially kinetic energy and momentum. The two main variables are M and V. So there was a correlation between kinetic energy and momentum that if both were conserved, then we could kind of use those two ideas together at times to form maybe a system of equations. We're going to do a similar idea in this one. So again, we have a oscillating system. There's a picture of it here where a block with mass M here is attached to a horizontal spring with force constant K, moving with simple harmonic motion, having an amplitude of a1. At the instant when the block passes through its equilibrium position right here. Remember, equilibrium position means the spring is not stretched or compressed, so there's no potential energy at that exact moment. It's all kinetic. At that moment, a lump of putty with mass little m is dropped onto the object, the block, and sticks to it. And what we have there is a collision. And anytime we have a collision, what should pop into our heads is possible conservation of momentum. And that would be actually elastic collision since it sticks to it, as it says here. All right, the first thing we're asked to find is new amplitude and period. And of course, we don't have any numbers, so we have to find it in terms of some of the original values here. And by the way, we're only going to complete part A. Part B just says repeat this same idea for a slightly different situation. I don't think there's need to do that. So we're just going to worry about part A, find the new amplitude and period from the described situation. So in part A, here's the same diagram that I made that was in your textbook. So we're going to first focus on what the energy is before the collision. So at that equilibrium position, before the putty actually strikes, it happens quickly. So everything's be at the equilibrium position. From the energy formula in this section, we can say that the total mechanical energy is 1/2 K times A sub 1, the defined amplitude squared. And we know we're at the equilibrium position. Therefore, as I said earlier, the potential energy is 0, and that means the energy is all connected. So the total energy, which can be at any minimum and always described by that, is equal to just K before the collision, which I'll define as K sub 1. Okay? So I could set those two things equal, and that means the V at that moment would be equal to this expression. Now, let's bring in conservation of momentum. Think conservation of momentum. I spelled think wrong. But anyways, before the collision, we have horizontal momentum on the x-axis only due to the block in SHM. Yes, the putty has momentum, but it's only on the y-axis. Remember, momentum's a vector, so we only care about the horizontal momentum here. So the putty has no horizontal momentum if dropped vertically on it. So before the collision, that's why we only have momentum horizontally x-axis due to the block. Then the putty strikes. Remember, the putty is mass little m and the block is mass big M, and they stick. So we would add their masses together and multiply them times a new velocity we'll call V2 after the collision. And just remember simple momentum, P equals mv. The total before equals the total after. Therefore, we could get an expression for V2 that's, if we solve this equation from above, V2 equals big M divided by big M plus little m times V1. Now let's go back to using this right now. So the energy after the collision, and remember, we're still at the equilibrium position. This all happens very quickly. So we won't be having any potential energy. This is all at the equilibrium position. So remember, due to that, it's only kinetic energy. And again, kinetic energy is 1/2 mv squared, but E2 represents after the collision. After the collision is 1/2 the total mass times this new velocity, which we found above in terms of V1. So we're going to sub in this V2, this expression here for this one, square it, and we'll clean it up a little bit. So this step is just plugging all that in. Maybe it gets a little ugly algebraically. And we could yield the expression for E2 right here. But 1/2 mv1 squared from really early in the problem is what energy 1 before the collision was defined as. So I could plug that in there. And remember, at any time, the total energy is 1/2 k times the amplitude squared. So E2 is just going to have amplitude 2. This is going to be the new amplitude. Once that putty gets dropped on top of it, it's not going to have the same amplitude as it progresses as it would have if that putty did not fall onto it. So now I finally have a kind of ugly expression I could solve for a sub 2 in terms of what I wanted. And one more substitution here, though, is that energy 1, defined earlier in the problem, E1 is 1/2 times the spring constant times a sub 1 squared. And now if I clean that all up and solve for a sub 2, I get this final expression. And I have it exactly in terms of what possible givens we had in terms of amplitude 1 and the 2 masses. The spring constant cancels out, so we don't need that hanging around anymore. So yeah, a lot of steps there, but hopefully that makes sense. And it correlates a little bit to some energy and momentum stuff we did linearly in the past as well, just applied to SHM. I did ask one other thing, but this part's easy. It wanted to find us the new time period too. But if we go to the formula given in the first section for SHM, T equals 2 pi the square root of m over k. The only thing we have to do for the time period, k is still the same spring constant even when that putty drops on it, k is the same. The only thing that changes is the total mass of the system. So instead of generically m there, it's going to be big M plus little m, and that will simply give the new time period. So again, a little bit of mathy substitution here got a little messy. If you take it step by step, it's not too bad.